Hello, Physics 1. Welcome back to part 2 of Wednesday's lecture. We are going to be starting Chapter 9, all about rotational kinetic energy and other types of kinetic energy. So we're going to be expanding the energy principle out further. All right, so here's a question to ponder. Can we analyze the motion of a frisbee or disc golf? So for those of you that like ultimate or who play disc golf, I do both terribly but enjoy them immensely. You know that when you throw a frisbee, it rotates and it also goes in a straight line. So we certainly know how to do this. We can do this. 1/2 mv squared, easy. So, however, we can't do this. Well, not yet. And this is the dilemma that we're going to be working on in solving in this chapter. We know things vibrate, we know they rotate, but we don't know how to handle those things yet. So let me give you a new term to get you started. The motion we know how to analyze, which is the motion of the center of mass. So this is called translational kinetic energy. So this is just translational kinetic energy. 1/2 mv squared, we were old hats at that. Okay, now let's do rotation and other fun things, because the learning never ends in this class. It's great. Okay, so if we're going to do different types of kinetic energy, we need to talk about the methods to do this. So we're going to talk about the separation of multi-particle system energies. All right, so I'll write out explicitly translational kinetic energy we will denote that as K sub TRANS, K-trans, or K-translational. This is the kinetic energy associated with motion of the COM, which is the center of mass. Then we have everything else. So this is relative kinetic energy. We will denote it as K sub rel. And this is kinetic energy relative to the center of mass. So for example, if we have two atoms in a molecule, they will have vibration, they might have rotation, and translational. So all of this vibration and rotation is relative kinetic energy. And the translational is, of course, translational. So that's what you think about it. So we've got translational and everything else. So the center, it's happening around the center of mass, but it's not the movement of the center of mass. Okay, so our expression for multiparticle energy K total is equal to K translational plus K relative. K relative is equal to K vibrational plus K rotational. All right, so let's talk about each one of these. Translational, including just a deeper discussion of what we already know how to do, which is translational kinetic energy. So this means to translate means to move from one place to another. And the velocity of the center of mass is denoted VCM. So this is, as a whole, what is the velocity? And if you recall, the position of the center of mass, RCM, is equal to M1 R1 plus M2 R2 plus M3 R3, and so on, divided by M total. So that is the location of COM, and then M total is equal to M1 plus M2 plus M3, and so on and so forth, adding up all the masses in the system. And if you recall further, back to when we used to see each other, the velocity of the center of mass is equal to M1 V1 plus M2 V2 plus M3, that's a V3, so on and so forth, divided by M total. All right, so, and then a couple other things just to remember. For velocities, much, much smaller than the speed of light, the momentum of the system is equal to the total mass times VCM. You should be well familiar with that equation at this point. And if we bring it around to energy, so K translational is equal to 1/2 M total VCM squared, which is equal to P squared of the system divided by 2M total. All right, so same thing we've been doing, we've just fleshed it out now to think about systems as more than just point particles. All right, so let's do an example. What is the translational kinetic energy of a 180-gram disc golf driver traveling at speed 17 meters per second? Yes, I looked up the actual weight of the driver disc, and I think this is like the average speed of a non-professional. So K translational is 1/2 M total V squared CM, 1/2 0.18 kilograms to convert grams to kilograms times 17 meters per second quantity squared, K translational, is equal to 26.01 joules. Now, is this the total kinetic energy of the disk? And hopefully you are way ahead of me. And you're like, no, it's rotating. But I don't know how to do that yet. Or maybe you do. Okay, we're getting there. But that is the translational kinetic energy. Moving on to vibrational. Building into rotational. Okay, the reason I'm going to do this next is we're already somewhat familiar with vibrational. So we could have our vibrating molecule. It's just, going up and down like a shake wake. It's got some vibrational energy. And so vibrational energy we saw this when we looked at spring systems. So E vibrational is just the kinetic energy vibrational plus the potential of the spring. Okay, so now we can combine this with the translational and kinetic system. So now we'll take our little vibrating molecule, so it's vibrating and translating, and so we can write the energy principle. So the E total is equal to 1/2 to m v squared cm plus K vibrational plus 1/2 KSS squared plus 2mc squared. And let's go ahead and identify. So this is translational. But we're now expressing it in terms of the center of mass. And remember, there are two molecules. Two atoms, twice the mass. This here, this is the vibrational. And this is rest. So we're not looking at delta E, we're just calculating the total energy. So rest mass is here to play. And once again, we see 2mc squared because there's two little masses. M here, M here. M total is equal to 2m. Okay, and one thing to note, these energies are not interdependent. So this is going to translate along. It could be exactly the same whether or not this is vibrating. That's independent of this vibration. Now, it will change obviously it changes the total energy, but there are two independent things to calculate. Okay, so moving on to rotational kinetic energy. So if we have a spinning disk, so it's going to have, let's say it's just spinning around in place. So the velocity of your center of mass is 0. It's not translating. It's just sitting there, just spinning in place. So think of maybe being on a spin bike, your back wheel is spinning, but you're not going anywhere. It definitely has kinetic energy. So it's going to have some relative velocity that's relative to the center of mass, but it's just you spin me right round, baby, right round. And I translate nowhere, baby, right round, round, round. That famous kinetic energy song from the 80s. All right, so The kinetic energy is not zero, even though the center of mass is not moving. It clearly has motion, but we don't know how to calculate this type of motion yet. So it has relative kinetic energy. So, and the type of relative kinetic energy, it has rotational. Rotational. And we will call it K rot, or K rotational. And this motion is relative to the center of mass. All right, so in the case of a bike wheel, my favorite kind of wheel, there's the tire, and then you've got some spokes. Okay, so almost all the mass is in the rim, traveling at speed v-rel. So this relative velocity, the velocity that it's going around, right round, like a record, this is what we mean by that relative velocity. So the kinetic energy of the wheel, K rotational, is approximately 1/2 mv squared relative. So this is still going to be the basic form for relative kinetic energy. And we are building towards a more thorough and complete calculation. So we're not quite there yet, but we're setting down this framework. Because it turns out that rotational kinetic energy gets a little bit complicated and is very system dependent. All right, so rotation, vibration, and translational. And by a more complete calculation, I mean the next lecture. All right, so let's go back to our vibrating, rotating, translating molecule. All right, so here's our molecule. We've seen it a few times. So the center of mass is about there, in between the two molecules. Okay, so another way we can think about parsing out different categories of kinetic energy. So internal kinetic energy. So that's not going to be translational. Separate into rotational and vibrational. So these are all things that are happening inside of this system. Okay, so we can now use this to further clarify our idea of momentum. So we can now we can classify momentum into tangential and radial. So radial is the component of motion in line with the center of mass. And I'll draw a picture here in a moment. Tangential is the component perpendicular to that line. So for our this would be radial. And this would be tangential. So we can see if it's vibrating in this direction, that would be a radial momentum. Nope. Nope, nope. No. Vibrational is associated with tangential, and radial is associated with rotation. All right, so for circular motion, around the center of mass, P radial is equal to 0. So P tangential is associated with vibration. So kinetic energy in these terms, P squared over 2m is equal to P squared tangential plus P squared radial divided by 2m, which is equal to K rotational plus K vibrational. And this brings us back to K relative being equal to K rotational plus K vibrational. So the total energy of a molecule is E total is equal to K translational plus K rotational plus K vibrational plus 1/2 Ks squared plus 2mc squared. And there you have it. So you have the potential, the spring-related potential between these two here, all of the kinetic energy, and then of course the rest mass. All right, so one thing to note, this isn't the only types of relative kinetic energy, but these are the most common ones. And the reason why we separate it out is actually because it just makes calculations much easier. It's all kinetic energy. Just like we just have very basic types of energy, sometimes we classify things out further because it makes calculations easier and it helps deepen our understanding. So this is all energy of motion. This is all kinetic energy. Just, we're categorizing it. Just like you might categorize your sweaters. All right, so let's look at the gravitational potential or gravitational energy of a multiparticle system. All right, so we have been treating objects like all their mass is in a central point. All right, so now we have expanded our systems, so we need a new approach. Or maybe this approach works. Let's find out. So let's consider a block. Got all these atoms in it. Each atom, mass m. And so let's look at, say, this one. So this is going to be m1, and it's some distance y1 above the Earth. Okay, so actually let's make this more generalized. So some atom mi, some distance yi above the Earth. So we're going to say, so the gravitational potential for this atom is MIGYI, and so UG is equal to M1GY1 plus M2GY2 plus M3GY3 plus so on and so forth, which is equal to G. We can factor that out. M1Y1 plus M2Y2 plus M3Y3, so on and so forth. This is basically just M total, so now we have, so My, center of mass, is equal to M1Y1 plus M2Y2 plus M3Y3, so on and so forth, which leads us to gravitational potential energy. UG is equal to mgy center of mass near Earth's surface. So actually, this is fine to go ahead and treat extended systems like the center of mass, or that the mass is all concentrated in terms of calculating potential energy. And that basically shows us that that's fine. As long as you don't have an object so large as to have a gravitational differential. So for example, if you had, I don't know, a battleship, like a destroyer from Star Wars. Why did I think I could draw this? I don't know. That was like 3 miles long. You might have enough of a, and then this is the surface of the Earth, you might have a little bit of a gravitational differential there that you might need to keep in account with. So that's what I mean by gravitational differential. All right, so we will end here for Wednesday's lecture, and Monday's lecture we will get into the nitty-gritty of rotational kinetic energy.